I'm explaining some important formulas from motion in straight line, that is one dimensional motion. So we will just look at in one dimension, that is x-axis. So first of all, to describe the motion of a particle in one dimension, we have to define velocity. So this first equation you can see here is the equation for velocity, which is average velocity. It is denoted by VAV. X, this subscript defines x-axis. So average x velocity is equal to change in distance displacement, which is denoted by delta x right here, divided by total time interval taken to travel that distance. Okay, so this is equal to delta x, which is the displacement. X displacement is given by x2, which is the final position, and this one is initial position. Okay, and the time interval is the final time and initial time. When particle is at x1 position, time is t1. When particle is at x2 position, time is t2. So t2 minus t1, and it was delta t. Okay, so this is the definition of average velocity. So this average velocity is the velocity over the time. Okay, so this second equation is the instantaneous velocity along the x-axis. So this will be the limit of here it should be delta t. Limit delta t is approaches to 0. That means instantaneous velocity means the velocity at a particular instant of time. That means we are not averaging the velocity at particular instant of time. Suppose at 1 second, what is the velocity? That's why we take limit of this one, delta x divided by delta t. Approaching delta t, very small. The meaning of delta t approaching to 0 does not mean delta t is exactly 0, but it is very close to 0. Okay, approaching 0. That gives you the instant of time, very small amount of time, right, at which you are measuring velocity. In your car, your speedometer show you instantaneous velocity. That is not a average velocity. That's why the speedometer showed you different value when you speed up or slow down. So this is equal to uh, rate of change of displacement given by here, dx divided by dt, that we call rate of change of displacement. Okay, so instantaneous rate of change of the particles x coordinate gives you the instantaneous x velocity. Okay, so this is the instantaneous x velocity. Similarly, we can define acceleration, x acceleration, average acceleration, and instantaneous acceleration. Look at this equation, which is average x acceleration. This is given by delta x, delta vx, that is change in velocity along x-axis, divided by delta t, the time interval that is taken to complete that velocity, right? To change the velocity, I mean. So that is equal to final velocity minus initial velocity divided by total time taken, which is given by t2 minus t1. Okay, so this is the average velocity of the uh, particle in any object that is in motion in one dimension. Similarly, you can define the instantaneous acceleration along the x-axis. It is denoted by ax, which is given by limit delta t approaches to 0, as like similar to the definition of the instantaneous x velocity. We have to set limit delta t approaches to 0, delta vx divided by delta t gives you the instantaneous acceleration. That is, it is actually the change of the particle's x velocity with respect to time, that is dv along x-axis divided by dt. So rate of change of velocity with respect to time gives you instantaneous velocity. So these are the very important formulas to be remembered, because without knowing velocity and acceleration, average velocity, average uh, instantaneous velocity and instantaneous acceleration, we don't know about the motion of an object. After knowing these parameters, these physical parameters, we can now go to the very important other formulas that are related to one-dimensional motion, which are called kinematic equations. So in this box right here, you can see the kinematic equations. Bunch of equations are there. There are 4 equations at all. And the first equation gives you the relationship between velocity and acceleration. Remember one thing, while deriving kinematic equations or dealing with the problems related to kinematic equations, uh, the acceleration is considered to be constant. That is, acceleration remains constant. That's why this is also the limitation of the kinematic equations, because if a particle is accelerating, we can't use these equations. Okay, remember this one, period. So Vx right here is the x velocity at time t of a particle with constant acceleration. Okay, this Vx. So this is equal to the x velocity of the particle at time 0 plus ax, which is constant acceleration of the particle, and multiplied by time. Okay, so this first equation gives you the relationship between uh, final velocity, initial velocity at time 0, at time t, this one, and at constant acceleration, and the time taken is t. Okay, if any one of these variables are unknown, you can find them out from known quantities, right? So now go to the second equation. This equation gives the position at time t of a particle with constant acceleration, right? At time t, it will tell you the position of the particle with constant acceleration. Okay, so this position will be given by x naught, which is position of the particle at time t naught, plus v naught x, which is x velocity of the particle at time t naught, plus half a x acceleration, which is constant t squared. You know, t is time, right? Similarly, there is another equation that relates final velocity, initial velocity, acceleration, x acceleration, which is constant, and position. Okay, so this one showed you x velocity at time t of a particle with constant x acceleration. Right. This one gives you x velocity of the particle at time 0 is constant x acceleration, and x naught is the position of the particle at time t naught. Okay, so these are the variables in this equation. Okay, now let's go to the another equation, which is which gives you the relationship between average velocity and the position of at time t of a particle with constant x acceleration is x, right? Position of the particle at time t naught is x naught. This is equal to average velocity. This half v naught x plus vx gives you the average velocity multiplied by time. This is simply, position is equal to velocity multiplied by time, right? So these are four very, very important equations we need to know to explain one-dimensional motion, that is particle that is moving in one dimension. It may be in x-axis. We are deriving here using x-axis. Okay, symbols are used for x-axis, but you can apply these equations along the y-axis, along the z-axis, or along any axis that is one dimensional. Okay, so what if acceleration is not constant? If acceleration is not constant, we can't use these equations. No, no, no. So what do? You must use calculus. That's why calculus is developed. If something is not uniform, that is changing with time, something changes there, then we can use calculus mathematics, which is very important mathematics devised by Newton and Laplace at the same time. Okay, so look at here these two equations, which are especially for non-uniform acceleration, that is particles are accelerating, acceleration is not constant. Okay, so uh, look at here px, which is the velocity 8 times t, which is equal to velocity 8 times t naught plus integration from 0 to, this sign right here is the sign of integration. If you are familiar with calculus mathematics, you understand this, right? It is integrating the acceleration from 0 time to time t, because at every moment of time acceleration is changing, right? Acceleration is changing, not constant. Okay, this is finding, actually this is the equation, the first equation, right? The just condition is different. Similarly, to find the position, you have to use again integration, right? This is the x position 8 times t, and this is the x position 8 times t naught plus integration from 0 to t, the velocity is changing, the bx dt. So this is for if velocity is not constant, we can use this equation. If velocity, sorry, if acceleration is not constant, you can use these equations. If acceleration is constant, we can use these equations. Okay,